Yeah, this would be the difference then between a positive work done by gravity and a negative work done by gravity. Okay, again, remember, if the force is going in the same direction as the object moving, then it is a positive work. So in the case of this lifting an object, you're dealing with two forces here now, right? The applied force versus gravitational force, whereas this one is all gravitational force. So in the lifting example, the work was done by the applied force, but the work done by gravity is negative. All right? Clear? Okay, let's take a look at this one here. Suppose the ball is now thrown up at an angle and then comes back again. You see what we're doing here? The stuff that you did in the beginning, it's coming back. We're wrapping it up. This unit, by the way, work and energy unit, wraps up everything in classical mechanics. So everything that is Newtonian physics, we're wrapping it up now in this unit because we're moving into modern physics after this unit. Okay? All right, so let's take a look at what's happening here. So you throw this object at an angle and then it's back down again. So what unit was that? It's thrown up at some angle, reaches maximum height, and then it goes back down. Projectile motion, right? And assuming it lands on the exact same level right there. Okay, so we're looking at this. This is now an angle. So let's say the ball is thrown up at an angle. So here we're looking at, that would be the applied force, right? You gotta kick it or throw it. So you have to put your applied force there at an angle. But how did the object move in this case? Well, first it was moving, well, there's two motion, right? There's the y component and the x component, right? So the object eventually moved from here to here, so it moved along the x, but it also traveled along the y to its maximum height. So if you're looking at the force that is in the beginning here, remember work is force times the delta D, right? So if you were to calculate the work done by the applied force in the beginning, initially at, let's call this at point 1, at point 2, and then at point 3, and then we're going to look at the total work done on the system, on the ball. Okay, so at point 1 right here, you could calculate the work done by the applied force, and how did the ball move? Well, the ball moved this way, right? So then you actually just take a look at, well, what is the distance traveled right there? That distance right there. So then you can easily just, if you say whatever distance that's been traveled by the ball, how much force did you apply? Okay. Now that applied force, by the way, okay, you're gonna have to, again, the applied force is, are you talking about the applied force on the x? You're talking about the applied force on the y, right? Because it is at an angle. So even though work is a scalar, right? Scalar doesn't have direction, force is a vector. So we still have to look at the cause of that work. Okay, what about at the very top and then at the very bottom? Well, again, the same thing. So the distance traveled will be, again, the distance traveled along the y and the distance traveled along the x. So we can consider that. So we can calculate those independently. But if we look at the total work done on this system, so starting from 1 all the way, reaching maximum height, and then going back down to the initial level that you started, kicking that ball, what is the total work done by this system? The total work done. So what are we talking about here, x or y? So if you look at from here to here, well, the ball went from here to here. We don't really care how the ball traveled, right? It went up and then it mirror imaged that in parabolic trajectory projectile, right? But we know that along the x-axis here, the ball moved from here to here. So what is the range? Now we're bringing in the projectile motion range calculation here. So what is the dx right there? And what was the force along the x? A force on the x. That would be the work done. And then along the y, what is the work done along the y? So that's the work done along the x, but what the work done along the y? Yeah, so F-A-Y delta D, the delta y. Well, what happens there? According to the vertical direction here, did it go back to the original? Yeah, it did. Vertically. It went from here, it went up, and then it went back down. So what's the delta y? 0. So the work done on the y is 0, vertically. That's what you were thinking, right? Because it went up and then it went back at the same level. So yeah, it is 0 along the y, but along the x, it traveled a certain distance. So we needed to look at those in terms of the x and y as well. Okay, gravity and the work energy theorem. Any questions so far? Okay, so now this is just throwing the ball straight up into the air. So here's your height of 1.2 meters. The ball reaches a maximum height. Oh, so this is actually the delta y from the beginning, 1, d1, and this is dy2. So we can calculate the delta y then, right? Falling back down, determine the speed of the ball as it comes back down. So we're looking for the v. Compare the speed with the speed of the throw. Okay? All right, so what's the delta d right here? So that will be the dy2 minus the dy1. What's that? We got 4.8, take away 1.2. What do we have? 3.6. So we have 3.6 meters, right? Okay, so we have the height here. So here's what happened. You take a ball. You're already at a height of 1.2 from the ground. So basically, this is like a person standing up. Take a ball and you throw it. You guys remember we were out there? We did that experiment. And then you throw it at a height to the maximum of 4.8 all the way. It says here the ball reaches a maximum height of 4.8 meters before falling back down. Okay, so falling back down and you're already at 1.2. Compare the speed with the speed of the throw. All right, so there's work done on the ball, right? And there's gonna be, it starts to determine the speed. So then we can calculate the kinetic energy there. Okay, so work is F delta D. So what do we know? We know the D, D1, D2. That's all we know, right? Okay. Okay, so what I'm gonna do here is work is F delta D is equal to 1/2 mv squared. Okay, what is the force here? Well, you're throwing it, so that will be the mass times the gravity times the delta D equals 1/2 mass v squared. We don't even need the mass, right? So we got the G, we have the delta D, and so we're calculating for the V. Okay, so the V then will be 2 times G times the delta D over, oh, that's it. 2 times G delta D, that's it, and square root, that's it, right? And that will give you the V. Okay, let's come up with the answer, and then let's talk about the, compare the speed with the speed of throw. Okay, here's the question. Before you plug in your numbers into your calculator, so here's the person, right? The person is holding the ball. The ball's already 1.2 meters. The ball reaches a maximum height of 4.8 meters. So that 4.8 meters, that's got to be measured from the ground, right? And then before falling back down, determine the speed of the ball as it comes back down. Now my question now is, do you think we're going to assume here that the person caught the ball? We're gonna have to assume that, right? Let's assume that, because otherwise the 4.8 is measured from the ground. It says a maximum height of 4.8 meters from the ground. Okay, so what do you think? So the delta D would be this one right here, right? So we're gonna assume that the person caught
the Volvo license number FFW745. Please come to the office. License number FFW745. Please come to the office.
So we're going to assume that we can answer it two ways. First, in my first answer, I'm going to look at the person caught the ball, just like what you guys did in your experiment. So that means the delta D traveled is just 3.6. Okay? So I'm going to put the 3.6 right here. So 2 times 9.8 times 3.6. Take the square root. You guys give me that number. And what do we have? Where's my 8.4 meters per second, right? Okay, so assuming that you did catch that, compare that with the speed of throw. What do you guys think? If this is the speed of catching it, what would be the speed of throw? So right here is 8.4. You caught it at 8.4 meters per second. Assuming this is an isolated system, this would have to be 8.4 meters per second as well. What is the V at the very top? The V would be 0. Okay? Again, negative G right here, positive G as it goes down. Okay? What if the question now, because it didn't clearly if the person caught the ball at the same level as 1.2, what if the ball went all the way down? What would be the difference here? What's going to happen to that 8.4 as it continues 1.2 meters more? It's going to be faster, definitely, right? So we can again answer two ways. We can say that if the person caught it at the height of 1.2, then it will be the same speed of throw. The speed of catching at 8.4 is equal to the speed of throw. You guys remember your projectile motion right here, right? Does that make sense that it is the same? When you throw the ball at 8.4, it's going to slow it down. It's going to stop at the very top because of negative G, and then it's going to speed up as it goes down at the same rate. So the same rate of speeding up is the same rate of slowing down. You're going to have the same speed of catching. But if you didn't catch it and you keep going all the way to the ground, it's going to go faster, which we can calculate that too. Make sense?
So
all right.
Compare the speed with the speed.